Hello everyone, welcome to the sessions on wired LANs. Whenever we say LAN, LAN refers to local area network, and the local area network is nothing but we are limiting our boundary, or we are limiting our networks to a geographic area such as buildings or campuses or colleges, schools, or any kind of a society which can have a limited geographic region of coverage area. We basically name that as a LAN. So now we are dealing with wired LANs, and most specifically we are stressing on the term Ethernet. So why this term Ethernet is because there are too many standards which are already available, or too many technologies which are already available in the market, which are like Ethernet, token bus, ATM LAN, and so many other technologies. But out of this, till date, what is the dominant kind of technology that is existing, and it is improvising itself in terms of data rates and all, is the only one standard technology which is Ethernet LAN. We can say that Ethernet, even though it has gone for 4 decades or 5 decades, or even though it has taken 4 generations of evolution, it is still remain the same, or its concepts of description is still remaining the same. So what is that we want to say here is, with respect to the needs of the market, with respect to the need of a customer, the user, the new technology here is improving, but with the very old basic concepts that were used in Ethernet. So Ethernet, it has not changed, the word remains same, but the technology usage and the customer needs are satisfied by improving the already existing technology, which is Ethernet. So now coming to the standards that are available, that is the IEEE standard, which is available for describing such kind of new technology, wired technology or wireless technology, or any kind of LAN protocol or metropolitan area network protocol. Any network protocol, it is always defined by a standard, which is IEEE standard. So the standard that has been given here for the Ethernet is what is Project 802. The number 802 is helpful for denoting the Ethernet. Depending on this 802, we have the next many versions like 802.1, 802.2, and so on. So this is one such project which was standardized by the IEEE people to at the very beginning of the Ethernet. When we compare this particular project 802, or when we compare this particular Ethernet standard with that of the OSI reference model that is already existing, or the TCP/IP model which is already existing, there is nothing much change in that particular OSI layer. Instead, this particular 802 stresses only on the functions of your physical layer, and it will also stress upon the function of the data link layer. So it is varying slightly with respect to the functions that are going to be present at the physical layer and data link layer, and all the other higher layers like your network layer, transport layer, presentation session layer, and application layer. So all these layers are going to remain the same with respect to functionality. There is slight modifications that is being done with respect to the functionalities of the physical layer and the data link layer in an OSI layer, in order to make that compatible, or in order to make that to work for the 802 project. So now let's move on to the topics that we are trying to discuss in this particular section, which is basically dependent on, as already told, only the thing that is varying is data link layer and physical layer. So let us jump into understanding how these two layers, which are going to differ from that of the already existing OSI model or the internet model that is present. So you can see that the data link layer is subdivided into two parts. One is the LLC, that is the logical link control, and one more is the MAC layer, which is medium access control. And this logical link control, you can see irrespective of the types of LANs that we are using. So irrespective of the type of LAN, Ethernet LAN or the token ring LAN or the token bus LAN or any other new technologies of LANs that we are trying to use, this logical link control layer is going to remain the same. It is not going to vary for different LAN connections. And then what is that we can observe in your medium access control is, in medium access control layer it is divided, or it is further very much specific about what kind of LAN technology we are trying to use. Either we are going to make use of an Ethernet MAC, or we are going to make use of an token ring, or we are going to make use of a token bus, or we are going to make use of a ATM LAN, anything, any kind of LAN technology which we are going to make use of. Depending on that, we are trying to have the distinguish or differentiation of the MAC layers being divided as per the technology. We all know that the data link control layer's responsibility is to mainly handle the process of framing, process of flow control, error control. So all these kinds of mechanisms are being handled or taken care by the data link layer. So out of these characteristics, or out of these performances which is being handled by our data link layer, what is the job of the LLC or the logical link control layer is, it is trying to handle the framing process. Framing. So the framing process is taken care, or it is one of the duty of the logical link control which is present here. So framing is handled in both the logical link control layer as well as in the MAC sublayer, but more oftenly it is considered, or this would be the main duty of your logical link control layer. At the data link layer, the LLC is taking care of framing process, but when it comes for the higher layers or the upper layers, the main aim of the LLC layer or the logical link control layer is to provide flow and error control mechanisms, which demands, or whichever the higher layer or the upper layer services require such kinds of flow control and error control mechanisms, then this LLC pitches in and it take care of both the kinds of flow and error control mechanism. And coming for the medium access methods or the medium access layer which is available here, so we have discussed in our previous session, or we have discussed in our previous chapter about the multiple access methods, which is basically the random access method, the controlled access method, and the channelization. So coming to controlled access method, where you have referred to polling, strobing, and then channelization method like TDM, FDM. So we have discussed all such kinds of multiple access methods, but here this MAC layer is very much specific to the access method that the LAN has to use. It is going to specify that which medium access control process will the LAN technology or the LAN uh, Ethernet LAN or token ring LAN or token bus or any other technology of a LAN which is the access method is going to make use of is specified at this particular layer of MAC. So for example, for our Ethernet MAC, we make use of the CSMA CD, that is carrier sense multiple access with collision detection, as a multiple access method. And coming for your token ring and the token bus, the method that is used either for your token ring or token bus as a multiple access method is token passing. Token passing is one of the method which is we have learned in our reservation mechanism. So the token passing method is being used for our token ring or token bus Ethernet LAN. So coming for the next layer, which is the physical layer. So in physical layer, you can see there are different physical layers which are being given here. Like for Ethernet, there is a different physical layer which is available, and then there is a token ring physical layer, then there is a token bus physical layer. So all the physical layers are different again for in each and individual type of LAN technology that we are going to make use of. What is that we have to notice is, although there are only one MAC sublayer for standard Ethernet which is present here, but there are here, as it is mentioned, there are going to be several standards, or there are going to be several standard Ethernet physical layer implementation which is going to be discussed, which we will be discussing at the very earliest. So the Ethernet, it is not only one single kind of standard which is existing as of now. We have again the subsections of the Ethernet. So each standardized method that is available, or the standardized technology that is available, like for standard Ethernet, fast Ethernet, gigabit Ethernet, depending on that we will be having the designing of the physical layer which is done. So that is why they have mentioned here as, for Ethernet physical layer, we have several such kind of implementations which are available, which are of different specifications. So moving on to the next slide, we have the HPLC frame, which is being compared with the LLC frame and the MAC frame that is existing. So we all know that HPLC is high level data link control protocol, which we have studied in the previous class. So the high level data link control protocol basically has an address uh, section, and then the control unit, and then we have the upper layer data which is being received, and then we have the frame check sequence which is present. So on the same lines, if I want to compare this HDLC with our LLC packet data unit, so even the LLC packet data unit is somewhat similar to that of the HDLC frame. What is the common thing that is existing is, we can see we have a control sublayer, and then we have the upper data layer which is present here. So and other things like other functionalities are taken care by the MAC layer. So what are the other functionalities means, the frame check sequence, so the header sequence and the MAC payload, all these kinds of tasks are being taken care by the MAC sublayer. But whereas when it comes for addressing is again taken care by our LLC PDU, that is the packet data unit of the logical link control layer. What is the addressing that it is doing here when compared to that of your address of the HDLC is, we have one thing which is present here, DSAP, and then we have one more thing which is SSAP. DSAP stands for Destination Service Access Point, and then SSAP stands for Source Service Access Point. So it is going to tell us, or these two are going to act as a header for us to reach the packet from one particular access point to the destination access point with the proper addressing mechanism being used. So which means we are basically doing the framing process here for the at the LLC packet data unit. Then discussing about the standard Ethernet which is available. In this particular topic of standard Ethernet, we are going to first look at the classification or the evolution of the Ethernet standards for the 4 generations, and then we are also going to look at the working process of the MAC sublayer and the physical layer by looking at the frame format of the MAC layer or the MAC sublayer that is existing. So moving on to the evolution of Ethernet, we have 4 evolutions so far, or the 4 generations so far. What is the 4 generations is, so the first generation, or the traditional Ethernet standard that was existing, it was with a data rate of 100 megabits per second, and then the second generation, it was called as fast Ethernet with a data rate of 100 Mbps, and then the third Ethernet with a third generation Ethernet was called as gigabit Ethernet with a data rate of 1 gigabits per second, and the fourth generation is with a data rate of 10 gigabits per second. So coming for the MAC frame, which is 802.3 MAC frame of an Ethernet, which is available, or the standard Ethernet that we are discussing here, is this Ethernet frame. It contains 7 fields actually. So the out of these 7 fields, the first is the preamble, and then we have the next field, which is start frame delimiter, and then we have the destination address, source address, and then we have the next one, which is length or type of the protocol data unit, that is PDU, type of the PDU that we are going to make use. So we are going to have the length being specified there, and then we have the next thing, which is upper layer data, or the data and padding segmentation, which is present there, and at the last we have the CRC, which is basically used for checking of the errors of the bits that it is going to receive. The first field, preamble, this particular field is going to be of 7 bytes as specified here. It is going to be of 7 bytes, which is 56 bits. So these 56 bits are going to be of alternating ones and zeros. This particular preamble is going to act as, or it is going to just alert the receiving system of the incoming frame, and it enables the synchronizing of the input timing bits. So it provides, mainly it is present for the sake of alerting the whole frame which is present, to state that there is a pattern, or there is a frame which is incoming, or there is a data which is incoming. To say that and to maintain the synchronicity, we have the preamble, and this preamble is actually added as at the physical layer, and it is not actually the part of the MAC frame. So this will be added only at the physical layer. And the next frame which is present is, or the next field which is present is the start of frame delimiter. So this SFD is of 1 byte which is refers to 8 bits. So this 1 byte is always a flag byte which is given as it is here, which is 10101011. So this, it is going to signal the beginning of the frame. So preamble is going to tell us that there is an incoming frame which is present, and next, to get ready for the coming frame, or enabling the synchronization of the input timings, we have the next frame, or we have the next field SFD, which will tell us that there is a frame which has started to enter into the frame bits. So then SFD also warns the stations or the station that this is the last chance for synchronization. So within the given period of time, if SFD field enters into picture, or this particular flag bit 10101011 enters into the picture, then it also warns the station that this is going to be the last chance for synchronization, if at all you want to look for the data transmission or data reception when connected to the internet. Out of this particular 8-bit sequence which is available, in this flag, the last 2 bits, that is 1 and 1, it is mainly used to alert the receiver that the next field is the destination address. The next field that you are going to enter into is the destination address. So the next field which we have is the destination address, which is of 6 bytes. So the main job of the destination field is it is going to tell the physical address, or it is going to have the physical address being read, or physical address being mentioned of the destination station, that destination station of which we are actually trying to receive the packet from. Then we have the source address. Source address is again of 6 bytes, and it contains the physical address of the sender of the packet from the main station. So whoever is going to be the main station, so from the main station this particular source address will be specified, that I am the person, or person A or device A is the station which is transmitting data to the device B. So either the device A's address or the device B's address has to be specified here in the given fields of source and destination addresses. So the next field is length, or the type of packet data unit field. So this particular field is of 2 bytes, and which is like or the Ethernet standard, it is going to use the length as well as the type of the packet data unit being specified by the upper layer whenever it makes use of the MAC sublayer. So it is going to use both these functionalities at a time in general, and the length or the size of this particular field is 2 bytes. So the next field is data field. So this field carries the data which is being encapsulated from the higher layers or the upper layers protocols. So its minimum size is 46 bytes and its maximum size is 1500 bytes. Minimum size is 46 bytes and the maximum size is 1500 bytes of your data field which is present. This is going to be the minimum value, and 1500 is going to be the maximum value, which we will see at the earlier why it is 46 byte and why it can go up to 1500 bytes. And then the last field that is present is the error detection field, which is going to help us to detect if at all any errors that are present, and its standard size is given as 4 bytes. And then this particular case, it is going to make use of CRC32. So in this particular minimum and maximum length of frame definitions that has to be given for a standard Ethernet, which is given here for the frame as the minimum frame length, it needs to be 64 bytes, and the maximum frame length, it needs to be 1518 bytes, out of which we already know that the minimum payload that it can carry is only 46 bytes, and the maximum payload it can carry is 1500 bytes. So as told earlier, like why we have to minimize, or why we have to say that the payload length has to be always 46 bytes and its maximum length has to be 1500 bytes for the data field, is because the standard says it has to maintain, or the Ethernet standard defines the maximum length of the frame to be of 1518 bytes and the minimum length to be 64 bytes. In this minimum length of the frame of 64 bytes, it also includes the header and the tailor as a part of it. So if at all we try to count, already the standardized bytes of the data are being given, which is 6 plus 6 plus 2 plus 4, which is basically going to be 18 bytes. So out of 64, if I remove this 18 bytes of the field, I am going to get the minimum size out as 46 bytes. So the minimum payload length it can be is 46 bytes. So if the upper layer packet is less than 46 bytes, what we can do is we can pad it. Padding means adding of the zeros. Padding is done to make up the difference. If at all it is 44 bytes, then the rest of the 2 bytes we are going to add zeros to the data that is present at the payload pattern. So that is why we call this particular field as data field as well as the padding field. We also know that the maximum frame length is 1518 bytes. So out of this 1518 bytes, I have already specified what should be the standard values of your CRC, length of PDU, source address, destination address. It is 18. So if I subtract 1518 out of your the standard values of the addresses which are already existing. So I'm going to have the bytes being mentioned, which is 1500 bytes. So that is what is going to be the maximum payload which the data field or the padding field can carry over. First of all, why we need to have the length restrictions here? So the maximum length restriction is done basically of two reasons. The first reason is memory was very expensive when Ethernet was designed. So that is why we have to put a restriction on maximum length, which helps us to reduce the size of the buffer. And the second reason is the maximum length restriction. It prevents one station from monopolizing the shared medium. Means it is not like one station keep on trying to share the data or keep on trying to make use of the data which is being shared in the given medium. So by blocking the other stations that have data to send, if say if at all we say we take an example, there are two paths which are available, and I will say that I want to make use of both the paths to transmit the data which is available with me. I can choose only one path. Why I have to choose two paths? So it is wastage of the another path that I am choosing to transmit the same set of data when in two lines. So in order to avoid such kind of blocking which is being done earlier for the other stations to transmit their data, so we are having a restriction on our maximum length of the given MAC frame which is present here. Now let us look at quickly glance or frame length. The minimum bytes it should be 64 bytes and the maximum bytes it can be 1518 bytes. Then moving on to the next thing, we have the example of an Ethernet address which is being represented here in an hexadecimal value. So as specified, either the destination address or the source address, it will be always there as a length of 6 bytes. So that length of 6 bytes is present here, which is nothing but 12 hexadigits or 48 bits. 6 bytes basically 1, 2, 3, 4, 5, 6. 6 bytes of data are present here, which is represented here as 06, 01, 02, 01, 2C, 4P. So we can make use of the, or we are going to make use of the hexadecimal notation for Ethernet addressing. Then moving on to the types of addresses I can do. I have three types of addressing which is done in case of your Ethernet MAC. One is unicast addressing, multicast addressing, and then the broadcast addressing. So out of the 6 byte addresses that are present in my first byte of the address unit, in my first section or first part of the address unit that is present, I am going to look at the last bit, which is the LSB. If that LSB, if it is turning out to be 0, we call that as the unicast address. And if the LSB is turning out to be 1, I call that as the multicast address. So now let us look at what if it has to be a broadcast address by taking an example. The broadcast destination address is a special case of the multicast address in which all the bits are 0. So out of the 6 bytes that is available, the first byte, in that first byte, all the bits has to be 1. All the bits has to be 1. If all the bits are 1, then we call such a address as broadcast destination address. So you can refer to these examples and understand the basics of how the addressing is done, unicast, multicast or broadcast addressing. And coming for how these addresses are sent out or how these addresses are being transmitted when we are trying to transmit on the channel. So coming for the first case, if you can see the address here is 47 20 1B 2E 08EE, which I want to send it out on the line. So always the rule that we follow is, if I am going for a byte by byte transmission, or the very first rule that we apply is the byte transmission. So always the byte transmission happens from left to right. Always the byte transmission is going to happen from left to right. This is for byte transmission. So then coming for bit transmission, how the bits are being transmitted. So if the bits are being transmitted, it is sent from right to left bit by bit. So right to left means first the bit 7 is sent, and then the bit 4 is sent. Then the bit 0 is sent, then 2 is sent. Right? So let us look at the example here. So you can see this is for the representation of your 47 which was present. So 47 is the first byte which is being transmitted, but out of that 7 here is first getting transmitted, bit transmitted, and then 4 is the next bit which is getting transmitted. And for the next 4 bits it is 0, and for the next bit it is 2. And likewise I have for the next bit which is B, and then I have the next bit which is 1. So when it is bit transmission, it is always the right to left transmission which is going to happen. So 7 will be transmitted first and then followed by 4. Thank you. Happy learning.